before we start the actual talk, I would like you to help me for something. Could you please stand up just for a while, all of you? Yeah. Yeah. Great. Now turn around either to your left or to your right and give a high five to your buddy, to the next one. And I'll do it here because I don't have buddy. Yes, thank you. Now you may sit down. My name is Boyan, and today we are going to talk about JavaScript. And I have to admit that I have a very difficult task today. Not only because I have to talk about JavaScript, but because I have to talk about JavaScript while there will be beer outside in a while. So I will try to keep it as concise as possible and to help you wait here until we all enjoy the beer afterwards. I want to start this talk some 20 years ago. 20 years ago, JavaScript was born. There was this guy, Brendan Eich, who only in 10 days managed to write JavaScript. And then the first version was actually not called JavaScript. Then after a couple of iterations, when it was first released in Netscape Navigator 2, it was released with the name as JavaScript, which was the first almost stable version, let's say it. If you don't remember how it was 20 years ago, I'm going to help you. It was something like this. Maybe most of you remember this nice green color. And these splash screens, at this time, all the applications had a splash screen, and then you had to wait maybe 4 or 5 minutes until the actual application loaded. But anyways, when you started Netscape Navigator, you will be able not just to browse the internet, but also to have some client-side actions, let's say. This was nice, the first step was done. What's happened next? Well, Microsoft, of course, is going to release, because they see that Netscape is already a step ahead, so they say, no, we should also have our own version. And they call it JScript. And it was first released in Internet Explorer 3. So this was already the first steps towards JavaScript. However, afterwards, JavaScript was proposed to be a standard. And the first version, called ECMA 262, was released in 1997. Afterwards, it was not really a stable version, but afterwards there were a couple of other iterations. Maybe know that today we have ECMAScript 5, and next ones are coming later. The next years, after the first standard version of JavaScript was released, didn't really happen anything special. JavaScript began to be used just maybe some simple stuff like hiding and showing elements or doing some really small actions on the client side. Until we got this one. JavaScript became really, really popular. And in 2007 and 2008, we already had on the left this big encyclopedia about JavaScript. And then we have also the good parts, which are unfortunately very small, but still they are there. And this is just a proof that JavaScript was getting on, and more people were involved into using it. You should agree with me that jQuery is really an era in the JavaScript. Why is that? Well, because JavaScript became so popular, but the browsers were so different from each other. They're implementing its own version, let's say. So then we had a problem because although we had the standard JavaScript, it wasn't really working the same way in the different browsers, and this was confusing for developers a lot. And then jQuery came with the unified API and helped us to do this. And even today, jQuery is still one of the most used JavaScript libraries. So it really helped, it really solved a big pain in our everyday. But it's not enough that JavaScript was on the client side. JavaScript even went to the server side. Why not? We could use the same language. Why can't we just use it everywhere? And then came Node. came exactly with this proposal. We should use JavaScript on all different places, both on the client side and the server side. And it is working. If you take a look at these statistics here taken from GitHub, you could see that from the last couple of years, JavaScript is #1 language used to build software with. So this is something tremendous. JavaScript has grown from a tiny piece of software written only in 10 days to something that everyone is using everywhere. If you take a look at this chart here, which shows the number of modules that we are building with JavaScript, you can see that the first one is the Node.js module repository, which is tremendously growing up and up, while the other repositories, they're very slowly accelerating. So this is again a proof that JavaScript is getting bigger and bigger, and a lot more attention is put into JavaScript. But what's next? Then we say, well, we have JavaScript from the client side, we have JavaScript on the server side, but we have mobile applications. And what do we build mobile applications with? Well, we have Android, we have iOS, Windows Phone. Can't we use JavaScript for this? Well, of course we can. And these are only just a couple of the examples of the frameworks that help us build mobile applications with JavaScript. There are tons of others as well. But this is, again, we are conquering another area where we are using JavaScript instead of something else. Because we want JavaScript to be our only language. We want to use it for everything. Well, that's great. JavaScript is indeed everywhere, and we are using it for a lot of things, as we saw. However, JavaScript is a bit problematic language. First of all, it is not really a nice language. It has some caveats with which developers should be really, really cautious with while we're developing. Furthermore, all the virtual machines, they are optimizing towards JavaScript. But then at the end, the parsing itself, because JavaScript is a textual presentation which is parsed, then this becomes a bottom because you can't really optimize it more. You reach a certain point and that's it. You can optimize the execution, but you can't really do anything more. So you're reaching some level, and that's your high level of what you could optimize with JavaScript. But you want more. We don't want to stay here. I would like to ask you, how many of you are writing JavaScript here? All right, that's great. How many of you are writing in JavaScript rather than TypeScript or any other language? Okay, just 1/3 of it. And that's exactly what we're doing. What we're doing is that we are actually writing in some other languages and then compiling to JavaScript. We're using CoffeeScript maybe, or TypeScript, or we're using Java or C#, and we're compiling to JavaScript. Why are we doing this? I mean, we are using JavaScript everywhere. Well, because JavaScript is a bit weird, as we already said. It has its specifics that we don't want to pay attention to, or it could be we want to abstract from. We want to focus on our logic instead of doing these issues. And we are already used to build applications with Java or C# or anything else. And we want to use our skills in order to compile this to JavaScript. Whoa, what else could we do? Can we use maybe C#, C++? Because everything today, or most of the stuff are written in C and C++. Can't we use this in order to compile to JavaScript? Well, the answer is hopefully yes, we can do this. And Mscripton is just one of the ways to do this. This project, what it does is it takes a C or C++ code source file, and it compiles it into JavaScript. And you could choose either to compile directly to JavaScript and execute it on Node, or you could create a web version for this and execute it in your browser. And what does it mean? Well, it means that we could take anything written in C or C++ and then compile it to JavaScript. Well, this is something tremendous, because it means that we could port any kind of software on the web now and run it in our browser. How does it look like? Well, if we take a look at this, which is hello world, written in C, we have just one print line, nothing special. And if you want to transfer it or compile this to JavaScript, how would it look like? Well, it's going to look like this. It is a bit scary, but don't worry. That's, of course, because we have to compile first all the standard IO library, and then all these operations, or this one line of operation that we have. And there, of course, yeah, there is a bit difference in the size of the produced source code, but this is not that bad. The real, actually, output is that we are getting JavaScript, because this is JavaScript here, and we could execute it in our node or in the browser, respectively. Of course, you know, in C and C++, we can work with file system maybe, and you know, JavaScript is sandbox, so we can't really, our browser doesn't really allow us to touch the file system, and hopefully it doesn't. So, of course, it's a bit different there because you're getting some virtualized file system. This means that you should load some files in the JavaScript and use them as a virtual files. But there are some, of course, some differences. But the real value is that we are getting some JavaScript code produced from C#, from C++. And what does it mean? Well, it means that we can take a real game engine and put it into the web. And open your browser and then start playing a game, your favorite game. And Mozilla and Epic did this already. Just in 4 days, they could port Unreal Game Engine 3 to the web. And if you go and you can check, it's really, of course, it's a bit slow because it's using WebGL, but once it progresses, it will become really something that many people are going to take advantage of. Because this is game, no one wants to install things. We want to run everything online already. Why should I download some big file and install it where I can just open my browser and start playing it right away? What is the next step now? We are doing this. However, this is still rather behind than being optimized. We could do something better. And then Mozilla, they started a project called asm, and this project wants to help porting software to the web, especially C and C++ programs to the web. So it is a relatively new project, and it is experimental. You could test it in one of the versions in Firefox right now. But what it is? Well, it uses JavaScript. So it is a subset of JavaScript, because the current version of JavaScript, it has some problems. It doesn't really work well with numbers. We don't really have numbers because everything is flowed there. Furthermore, we have just-in-time compilation because we are using variables that can change type, basically. You can take one variable, have a number there, and then you can change and put some string into it. So this means that you can't really predict the type of this variable, and you can't really use some optimizations. So this is why we have just-in-time compilation. But then asm wants to actually take another path. Well, we will be using JavaScript, a different version or a subset of JavaScript, but we're using some, let's say, we're going to cheat a bit to help achieve ahead-of-time compilations. Basically, we are going to introduce some types in a way that we can have a system to understand them and give us some optimizations in the past. How could this look like? Well, this is something like this. An asm defines a module here, and it has 3 input variables. We have the standard library, which includes some basic JavaScript operations, for example, mat object. We have a foreign, which is a collection of some foreign modules that someone else has written. And then we have our heap, which is basically where we use our memory. And what we use this use asm. If you have used another protocol, use strict rules when you've been writing JavaScript. This is the same principle. And here we define our function, and then we export something, be it a function or constant or anyways. So this is a perfectly valid JavaScript code. But then if you look a bit closer, then you note some weird stuff. For example, if we take a look at the function area, you can see that it takes one parameter r, but then the first line we say r equals r or 0. Well, this operation is always going to return r, of course. So why? It's a bit weird, but the meaning is that we say here r is going to be an integer. Because asm is going to read this and going to think, okay, r is going to be an integer, so I'm going to optimize this variable for being an integer. Then we're using plus here when we return the result, which means that this is going to be a double. So we say, all right, this number is going to be always double. By using these small tricks, we could allow this ahead of time compilation. Basically, we could optimize our variables and make it run much faster. And if you had to run this as a normal JavaScript, for example, code, how could you do? Well, it is very easy. We basically instantiate our heap, which is array buffer. You could initiate it with anything you want there, basically. And then you just give it a window as our standard library, and then you could just call it. So it is a perfectly valid JavaScript that you could call and use. How fast is that if we are doing this? Well, if we take a look at these statistics here, we could see that if we get some C or C++ applications here and write them in asm, then you could see that this is here is the Firefox without asm. So it is pretty okay. Chrome is not really doing very well. Well, it depends on the application, of course. But then if you get the red one, this is Firefox plus asm. So you could see that it is really, really faster. And the green one is the native. Basically how the application itself is running under the native code, basically C and C++. So you could see that the asm optimization is very, very close to native. Very, very close. Maybe 1.2 times slower than it, but much, much better than without the asm optimization. The good thing about it is that because it is JavaScript, even if your browser doesn't support asm, it will just still run. Of course, it will be much slower, but it will run, so you will not lose anything there. Asm looks really nice. However, it has some issues with it. First of all, it is started by Mozilla. Although Mozilla is a really huge community, also other people joined the project, it is one of the big players who started the project. And we have had similar examples, and we know that if we don't get the support of all the community, all the big players there, it is really, really hard to get it through. Furthermore, as we saw, once the virtual machines optimize the execution, then we get the parser, because JavaScript should be parsed. And this can't really optimize much more, because it's a textual language. And when we want to do games, for example, or want to do some video on the web, you know that we want to do the things in a different way. We want to do things, to express them with a bit more mathematically, let's say. This is not what JavaScript is really made for. So we can't really have this flexibility. We could do this, but we have to do some weird hacks in order to achieve this. So what is the next step? Well, we could do much better than this. And that's why we get to the point where WebAssembly comes into play. And this talk today is going to be about what WebAssembly brings us and how we should take advantage of it to write some high-performance code for the web. So what exactly is WebAssembly? Well, WebAssembly is a new language, basically. It's a new language, and it is going to help us to express some mathematically, let's say, oriented code on the web. Code which requires a lot of optimization. It requires a lot of performance on the web. It is a great addition to JavaScript and to the browser because it will add some new features there and help us, developers, use it as a tool to make some interesting applications, like writing games, for example. If we had asm, then the short name for this one is wasm, of course, so that we could use it when we talk to our friends instead of saying WebAssembly, WebAssembly, WebAssembly. We could use wasm. It's a bit more, let's say, it sounds a bit better. The difference here, however, is that it's a collaborative effort, which means that now we have all the players that are supporting this project. So it's not only Mozilla, it's Microsoft, it's Chrome, it's Apple, plus a lot of other people contributing to this project. So this is something different now, because now everyone is interested into this project, and everyone wants to put effort into this project. Now, this means something much more to the community. It means much more to us, because this is something that we can rely on. It could probably survive into the future. There are some misconceptions that WebAssembly is the new bytecode of the web. But actually, it is not a bytecode, because bytecode is typically register-based. You don't really have this syntax there. WebAssembly is going to have its own syntax, because it's going to define an abstract syntax tree, as we're going to see in a while. And like JavaScript, WebAssembly is not going to be versioned, which means that instead of checking which version your language is, you're going to check for feature, basically. If you need to do something special, you would check, as you do in JavaScript, does this feature exist? And then you could use it. So it will reuse this flexibility that we have already with JavaScript to a certain amount. Another interesting thing is that WebAssembly will probably lead to a universal virtual machine. Why is that? Well, although we have these virtual machines right now, and they're doing almost the same thing, and they can almost optimize to the same level of executing JavaScript. When we have WebAssembly, this will actually unite all these players, because it will give them a standard point, one standard point. And this is something very important. WebAssembly defines its own abstract syntax tree. Basically, we will have some expressions that are linked together as another language. The difference here is that WebAssembly is going to have two representations, a text format and a binary format. So our abstract syntax tree is going to be represented in a binary format. And this is a bit different. So why would we do this? Well, the binary format is going to be basically a serialization of the text format. And this means that the browsers will be able to code it much faster than parsing a textual format. So this is a huge step from parsing into decoding something that is really there. You could think of the binary format as when you're writing JavaScript, for example, and then you're doing some minification of your code. This minification is basically replacing all your variables with ABCD, your function names with GFH, or something like this. Well, this binary serialization is going to do the same. Basically, it's going to replace your function with a number. And it will allow the browser to access the function itself from an array instead of calling it using a textual name. However, why do we need then a textual presentation? Well, if you, let's say, open your Chrome developer tools, you would love to see something there. If you see just some zeros and ones, it's not really going to help you. But if you see a textual presentation, then yes, maybe this is going to work now. And the cool thing is that what we want to do, if we are compiling from C code, when we open the browser, we want to see actually our C code, which will be the best. And this will be possible with the so-called source maps as we're using today. But if we don't have the source map, we could use the textual representation of WebAssembly. You should pay attention that browser is not going to parse the text. So this is only for us to help us. The browser is only going to work with the binary representation, because this is the fastest that we want to do. And it doesn't give us any benefit if we use the textual version when we have this optimization in place, which is one of the main ideas behind WebAssembly. How is this going to look like? Well, the syntax is not really defined yet, but this could be something that WebAssembly is going to look like. So we'll have some modules, we will have some functions, we could import some functions, call some functions. Maybe it doesn't really look nice. I don't know, maybe some of you would think, well, this is great hack code. I really want to write code with this language. This is up to you. You can decide to do it or not. But still in the process of defining how the syntax is going to look like, there will be some iterations about, and the community is going to give the votes to the different versions. There are a couple of other variations to this syntax, but it could be something like this. But then how are we going to produce WebAssembly? Well, you have a couple of possibilities. You could either write the textual presentation, basically you could write the thing that we saw just a bit, or you could programmatically create the binary representation just straight away using some software. But most of the cases and the main idea behind WebAssembly, it should become a compilation target from other languages, mainly from C and C++ in the beginning. So you will be writing your programs as you do today in C#, maybe Java or something else, C, and then you would use some compiler to compile this directly into the binary form of WebAssembly instead of writing it right away. And then that's why it's important that you have some source maps to debug this afterwards, because you saw if you compile C code to JavaScript, that you get something that is not really what you would expect you would get there. The good thing is that assembly is going to reuse much of the JavaScript world today. We already mentioned about the versioning, but another very important thing is that WebAssembly is going to be sandboxed as well as JavaScript is. And this is very important for security reasons. So when we execute WebAssembly, it will run into our sandbox there, and we could make sure that it's not going to damage our system. And this is, of course, not what we want. So there is nothing to be worried about here. Everything is under control for now, or at least according to the documentation and the community. What is the difference now? If we take a look at asm and WebAssembly, this is one of the Unity games which was written here. And you could see that if we write it in asm, we have this game is 19 megabytes. The same game written in WebAssembly, it's just around 6 megabytes, which is a huge difference. Now, what if we compress it? asm is JavaScript. So the way we compress it is, for example, JZip. This is a generic compression tool. And we got it from 19 up to 4.1. However, the compressed version of WebAssembly is the binary format, because that's why we have it, because this is our compression tool. And it goes from 6 to up to 3. So not that big difference, but still, if you compare the same game, it is less in size and much easier to keep track of what is going on there. WebAssembly is in the prototypical phase. Basically, there is a prototype built, so-called minimal viable product, to demonstrate the features of this project. And a lot of people are basically contributing to it, trying to take it a step further. We could use mscripten the way we saw it to compile from C code to JavaScript. We could actually use it to compile directly to WebAssembly, so you could actually experiment with it, and it is really easy to do this. You could actually try it even in a browser, because there is a polyfill developed for this. So even if your browser, as most of the browsers, doesn't support this yet, if it's not some special version built with this, but you could actually use it to test it in your browser. The good thing is that JavaScript is going to survive. Many people will become a bit afraid of that WebAssembly is going to conquer the web and kill JavaScript. No, it's not going to happen this. JavaScript is here and it will stay here as long as it is needed. Because WebAssembly is another feature to JavaScript. Because both of them are going to coexist. Both of them are going to be compiled actually to the real bytecode afterwards, which is executed by your machine code. So what we're going to use WebAssembly for is this weird stuff, like if you want to do some gaming, some video decoders on the web, then we could use this and write it in WebAssembly. We could still write our code in JavaScript, and we could use the modules written in WebAssembly. So these two are actually going to coexist quite well. So what is going to happen now? Well, as I mentioned, this is still a prototypical phase for WebAssembly. The main idea for it is that it should become a compilation target mainly from C and C++ code. It is going to support mathematical operations, and the future is going to bring the so-called SIMD. Basically, we want to be able to use parallel instructions. So if you have many computations, why don't and they're independent, of course, we could execute them together parallel. So this will give us a lot of performance benefits. WebAssembly feels these parts that are a bit awkward to do with JavaScript today. JavaScript is still helping us to do some logic, client-side logic, communicate with the server, with some web services, doing some animations. WebAssembly is going to fill the gaps that are not really nice to do with JavaScript. This year at the conference, the regular conference of Apple, they said, when they introduced their Swift language, they said that we really like Swift and we think it should be everywhere. And then the community basically reacted to this. Well, everywhere we already have JavaScript. We saw we have it on the client side, on the server side. We have it in the mobile web. Why do you think this? But then you can think now with the introduction of WebAssembly, we will be able to compile from Swift to the web. So you shouldn't laugh to people when they say something. Thank you.